Oh, hello. Eric Darling here with Darling Data. We will be doing a little bit more T-SQLing here. We're going to continue to talk about isolation levels. In this video, I'm going to show you how a read query under the default locking read committed isolation level can block a modification query also running under the default read committed locking isolation level. If you've watched a lot of my videos in the past, you may have come across this demo before. There are a couple of things that I'm going to show you that are slightly different in this one, but for the most part, it's going to be a very similar demo because there's no way to improve upon perfection. And so we're just going to go with this one. This is, of course, a small bit of the material from my T-SQL course. All 23 hours of the beginner content is published. The course is available still at the pre-sale price of $250 for life, and the value of this course will double to $500 after the summer when the advanced material comes out. So, of course, buy now, save now, or something like that, right? Something salesy. Something that entices you to click the buy button, right? Something along those lines. So I've got a store procedure here, and there's nothing terribly interesting about it. There is one parameter that gets passed in called start date that gets used down here. And there is just a simple, basically value assignment going on here. This is just to catch all the rows that come out so we don't have to wait for them to come out to Management Studio. It doesn't materially have anything to do with the demo. And there is, of course, go away. There is, of course, an index hint here just for demo stability. Just so you know, it's annoying when you hit F5 and you're like, oh, I got the wrong plan that time. Never mind. Cancel that. Cut. All right, do over. Try that again. So what I want to show you first is an example of where a query plan where this won't happen, even though it has the same plan shape. So let's run this and let's look at the execution plan real quick. Now, this version of the execution plan will look very, very much the same as the version I'm about to show you where there is a problem. There's going to be one material difference with the nested loops join operator. And what that is over here, this one does have the optimized equals true property, and you can see it sometimes for this, but not in this case, because there is no prefetch for this one. It's difficult to show you the absence of something, but just trust me, when I show you the actual one, there will be another thing down here that says unordered prefetch. This, of course, can happen with ordered prefetch too, but it's the unordered prefetch that happens for this one. Maybe, it could be the ordered prefetch, who knows? But because SQL Server does not estimate that at least 25 rows will come out of here, we do not get the prefetch optimization here. And that's the bigger thing to watch out for. So let's come over here and let's rerun this just so we can start with a freshly compiled plan. And now let's run this query with this parameter instead. So instead of 99991231, we're going to do 20131231, which is going to get us about 3,800 rows from here, but SQL Server estimates almost 13,000. So the big difference between these two is in the properties of the nested loops. Now we have this thing that we didn't have before. It's still optimized. Up here, you still see optimized equals true, but the bigger deal is the unordered prefetch down here. I'm getting slowly better at drawing arrows with this thing. Someday I'll be a Zoom It Pro. But this is really what causes the locking issue that we're going to see on top of the plan shape generally. So the real thing that goes on here is that when SQL Server uses the optimized, uses the prefetch optimization with nested loops, the locks on the clustered index accumulate to an object or escalate to an object level shared lock. So the entire time that we're running this query, SQL Server will hold on to that object level shared lock on the clustered index. The reason for that is because this query is really happening in two parts. You have an index seek over here into the non-clustered index. This finds all the rows that our where clause cares about. But then we have to do a lookup down here, and the lookup is to output the column post ID. the column post ID was not part of the non-clustered index that we have. So in this case, a solution for the issue would, of course, be to extend the index to add the post ID column to it. But what I mean by this thing happens in two parts is that SQL Server will do an index seek, and it will start finding rows here. For every row that comes out of here, SQL Server goes into this loop join, and from that loop join, we do a lookup to the clustered index. So for this, even though SQL Server is estimating almost 13,000, in reality, we do about 3,800 lookups to 3,800 loops to come down here and get stuff. While all this is happening, SQL Server needs to protect what's happening here. Right? So SQL Server needs to make sure that any rows we find here do not change or disappear in some way here. One way to do that is to take out an object level shared lock. You remember a video or two ago I showed you like a lock compatibility thing. And the object level, if you were paying attention there, the object level shared lock is incompatible with modifications. So SQL Server protects the clustered index so that rows coming out of here cannot change before this is complete. Right, so we're getting rows here, we're looping here, we're getting a column out of the clustered index. SQL Server basically needs to make sure that no one says, hey, let's drop that column, that post ID column, and also SQL Server no other queries come along and either update or delete values that would make would invalidate a row that we found in the lookup. So let's exacerbate this in a fun way, right? So this ran very quickly. This finished in 8 milliseconds. This did not run long. The 3,800 or so rows that we cared about didn't really do much of anything. But now, if we were to run this for a much larger number of rows, now this is going to be a parameter sniffing issue. And you might be wondering, well, Erik, you're on SQL Server 2022, and Erik, you're in database compatibility level 2016, and Erik, won't the parameter sensitive plan optimization kick in and ruin this demo and ruin your life? And the answer is no, because the parameter sensitive plan optimization does not work for, or rather, let's just make this easy. It only works for equality predicates, and only one of them. So this being a range predicate, a greater than or equal to, the parameter sensitive plan optimization doesn't do anything here. I haven't really tested this with SQL Server 2025 with the new optional parameter thing and the, what do you call it? I haven't really tested this with the optimized locking bit either. So who knows, maybe that'll solve all our problems. But if what we're going to do is we're going to run this. Over here, we're going to start an update in a transaction. Now, because I have accelerated database recovery on, this does not take very long to roll back or do anything with once the demo is complete. But then we're also going to come over here and we're going to run sp who is active. Now, having done this many times before, this should all go on for about 10 or 11 seconds. So I'm just going to run sp who is active until we get up to about 9 or so seconds. Over here in this window, what I wanted to show you with just the estimated plan here is we scan the clustered index here, and then we update the clustered index here. The update that we're doing in this, where we're updating user ID, that only affects the clustered index. We are not also updating that non-clustered index that we had. The only thing that gets updated in here is this. So let's come over here. Let's start running this. Let's start running this, and let's start running who is active. And we're going to get this up to about 9 seconds. That's close enough. All right, cool. So let's cancel this and let's roll this back. And let's see what happened here. So this query went and ran, and this took about, 12 seconds that time, almost 13 seconds. Look at that. Oh, that was close, right? Not bad. So this query took about 13 seconds, which means I could have gotten a couple more who is active runs out of this over here, but we're at about 9.5 seconds here. So you can probably understand and infer at this point that locking would have gone on, actually went on for about 13 seconds, like the entire time that select query was running. If you look at what was happening, you're going to say, oh, that's weird. There's a select query, And that select query is running, it's doing stuff. And then down here we have this update query. And this update query is waiting to get an intent exclusive lock. It is waiting to get an intent exclusive lock on the basically essentially the clustered index of the votes table. But it is being forced to wait. Right? This intent exclusive lock cannot take the locks that it wants. It is waiting. And the whole time that it is waiting, it is because this query over here, and we can get rid of the tempdb bit, this query here has an object level shared lock that has been granted on the votes table. So that object level shared lock is from the lookup portion of the plan with the prefetch optimization. So going along with all of the the normal blocking that we think about with the read committed locking isolation level, where modification queries will block write queries trying to take shared locks unless they have a no lock hint or something on them. Read queries, when they take an object level shared lock, can also block write queries from taking their intent exclusive and exclusive locks. So read committed is a very, very big whammy in a lot of ways. There is a lot of very, very dumb blocking that goes on that normal people don't want to deal with and struggle with. And so this is why the no lock and read uncommitted stuff sort of proliferates in the SQL Server community. Everyone loves taking shots at and dunking on no lock and read uncommitted, which of course, it makes them feel good. It makes them feel like they're smart. But what they don't offer is any sort of real suggestion or alternative to fix it. But on top of that, the thing that a lot of people fail to realize is that read uncommitted or no lock hints aren't the problem. The problem is that read committed locking is crappy. Awful things happen under it. If read committed locking were just not so awful in all these situations, people wouldn't be running off to no lock and read uncommitted. So there are some things to think about. Of course, there are ways to fix this particular type of blocking. If you extend the index to cover the post ID column, that would be one way. You can't change the type of join that a key lookup does. It's always going to be nested loops. You can't do a hash or merge join with a lookup. And of course, if we added a no lock hint to our read query, this would also be avoided. But I think, of course, the more professional and the more widely applicable way of fixing this issue is with using a row versioning isolation level like read committed snapshot isolation or snapshot isolation. Those will take care of all of these problems. So anyway, with that out of the way, thank you for watching. I hope you enjoyed yourselves. I hope you learned something. And I will see you in the next video where I will show you a read query deadlocking with a write query. It'll be somewhat similar to the first deadlocking scenario that I showed you, except we will only need one table for this one. We will not need two tables for this one. So it'll be extra fun. All right. Thank you for watching.